Welcome back. This is Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell for this series and a bunch of other ones on our channel. We're doing Linear Algebra 1. This is Chapter 1, Systems of Linear Equations. We're going to start Section 1.2, which is going to be one equation and one unknown and a complete analysis of that. Yeah, and everyone laughs at first because when you see it's going to have two variables and one equation symbol and one unknown variable x. We're probably going to call it like, how complicated can that be? It's the crux for all of everything that we do in Gaussian-Jordan elimination. If you pay attention to how he actually does this, and he uses one equation all the way the whole time. So we'll really pay attention to one equation and one unknown, and then eventually use it for all the other size systems of equations. All right, so first of all, let's start right at the basics. Some of the statements I get from students is, oh, I don't know anything about math, so maybe I should just, that you're trying to give a disclaimer so that you can't try. Well, good, because I'm also assuming that we're starting with 0, and then we'll start right from what is an equation actually. Let's point it out. It's just what you thought, but just in case. An equation is meant to denote the fact that two mathematical expressions are equal. Yeah, I used equal in equation, and it seems like I used the definition, the word in to define the word, but that's as close as we can get. It's intuitively what you mean. An equation is meant to denote the fact that two mathematical expressions are equal. For example, as our two pedagogical ones, which are basic, we get to do Barney math. Yes, 2 plus 2 is 4. In rhetoric, before they had, remember, this is the power of algebra. This is Al-Khwarizmi. It does this in about 600 AD. He invents algebra, and then equals took quite a while also. But in rhetoric, the sum of 2, the number 2 with itself, is another integer called 4. And as an equation, we're going to end up writing, first of all, there's the equal sign. You can't call it an equation if you don't have an equal sign. At the beginning of Rick and Morty is not an equation. That's a mathematical expression, yes, but I don't see an equal sign anymore. If I do this, then we're in business. And we're in a binary, should probably start at the front of the back, but it doesn't matter. Anyways, equals is this guy, and of course notice that this is not a binary operation, this is a binary relation. A binary operation creates a new thing from two things. A binary relation is either true or false. So this statement is either a true, it doesn't create anything new necessarily. What it's trying to say is this side is equal to this side, and this is a bad statement. So every equation that we get is going to be either true or false. Is what I'm trying to say with that. If we have a statement now, instead of writing this is clearly a false. I hope you agree that this is a false statement, so we don't write that. We put the dash, and we're going to put the dash or any kind of not equal in any scenario. Now let's get to the systematic demographic of all the scenarios of the most general case of what the heck is a one equation and one unknown, and what do we mean by linear. All right, for one equation and one unknown, this will be the same as we get more and more equations and more unknowns, but I'll go through all the terminology just in case at the beginning. Unknowns, usually at first we represent with x and y and z. So when I do a system of one equation and one unknown, or two equations and two unknowns, or and then 3 by 3 systems, etc., I'm probably just going to use x, y, z, or x, y, z. Once we get a system like Carl Friedrich Gauss gets, where he's got 28 unknowns or something like this to find the orbit of Ceres in our asteroid belt, and I run out of letters real fast, so I have to start indexing. So we may also use x or a single variable and then just index it, so we can say we have as many unknowns as we want. So usually for the unknowns, we use the end of the alphabet, x, y, z. For constants and fixed numbers in the equations, I know at first you're like, well, these look like unknowns and these look like unknowns, but these are the things we're actually looking for in the equations. These will be fixed in the problems. Specifically here, I have two equations in one unknown, and we're going to compare them. This equation has an x squared term, or actually what that is technically x times x, and then equals 2x. This is a term and this is a term. So first of all, a term is anything separated by an equals or a plus. 3 plus 3, those are both terms. 3 times 3 is one term. So it's the plus or minus or equals that gives you a term. Then what we want to look at is, what's the difference between this equation? Why am I going to call this one non-linear and this one linear? I'll give a more generalized definition of a general equation in any unknowns and what that means to be linear, but it's still essentially the same. An equation is linear if every term now, something separated by plus, minus, or equals, is either a constant term, so one of these guys, and it'll be fixed in the number 2, there he is, he's a constant term, or a multiple of a single unknown. This guy, 3 times x, that's a single term. And in general, that's what they're trying to say in rhetoric, is every term should look like a single multiple of a single variable. So then yes, you could change it to, if you have x, y, z, you could have this. You could have an a, y, or an a, b, or you can have a times b, or that would just be constant, or you can have a times y, or any one of these, but you can have 2 of them. And you're not allowed specifically to have, even if it's the same, this has x and x in the same term, and that's not linear. So this is not linear. And this is the reason why this term is fine. But this one's good. This is a multiple of a single variable, and this is a constant term. So this is a linear equation, and this is nonlinear. And this is what we mean in all mathematical contexts. An equation is linear if everything is either a constant or a multiple of a single variable. If we're now going to consider one linear equation and one unknown x, we have an equation. It has the unknown variable x in it. Otherwise, it's not an equation that has a variable x. It'll just be some tautology. So it has to have the variable x in it. Once we have that, we know that by our definition of linear, every term has to be a multiple of that only unknown variable x, or a constant term. And after we group everything together, I always say it in rhetoric and everyone like sort of nods, but it's like, do you really know what I'm saying when I say that? After you group all the terms together, I can just write like this. I can write ax equals b. And so just in case you don't see, this is what I'm saying. If I have a linear equation in one unknown, then I have 7x's. That's a term that has a multiple of x. This is a constant term. This is a multiple of x. This is a constant term. After I do algebra and group everything together, I can write it as ax equals b. With numbers in there, now you can see what we mean mathematically is, yes, for you, they're like, these are unknowns and these are unknowns. In our generic description of what a most general one equation and one unknown would look like. But as soon as you have a real equation, the a and b are fixed numbers now. He's the guy I'm looking for. And depending on which set of numbers you're looking for, also I stuck this in there, that means b is a real number and a is a real number. Element of the real, the set of all real numbers, just in case. So my point being, and why I remember that, was if you're looking for the solution in the real numbers, then there is a unique solution to this. If you're looking for this solution as a Diophantine equation, no. Diophantine means I'm looking for integer solutions. So the unique solution to this, you would probably say, is going to be 5/2. If you're looking in a real number where fractions exist, if you're looking for a whole number, then there are no solutions to this equation. So the same equation can have solutions or not have solutions depending on where I'm looking for solutions in which set. First of all, and I would not write this like this, I'm going to show you why we're going to write it like this. The inverse of 2 times 5. Let's do that. All right, looking at this most general equation of one equation and one unknown x, what we're going to do is solve for x is the idea in all of these, or solve for x and y, or solve for the unknowns. First of all, we'll give these more rigorous definitions once we have a handle on what systems are and that kind of thing, once we've done a few videos. But for now, anytime a mathematician comes at you and says solve this, they mean find all the solutions to that scenario. So you have to figure out what it means to be a solution in this particular scenario of whatever we're doing in math. And then when we say solve, we mean find all of them, not one or some or most, all of them. Luckily for us, here I get to say it again, is when we do linear systems, I don't care how big it is and how many equations or how many unknowns, there's only ever one solution, no solution, or infinitely many solutions. And this will be nice. It gives you a peace of mind. And then once you get used to this a little bit, other restrictions will also allow you to say, well, if there's only 3 options ever, and I have this scenario where I could sometimes eliminate other options, and then it's really easy to tell whether I'm going to have one solution or nothing, and then find them. This will be the idea. That was a long-winded way of saying solve means find them all. In one equation and one unknown, there will be at most one solution. I have at most 10 BMWs, which means I could have 0, which is a true statement. Case 1, what we're going to do is we're going to do 4 cases based on whether A and B are 0 or not 0. 2 of these cases will look awfully similar because of, well, we'll go through them. In the first case, what we have is we're going to assume a priori that A is not 0 and B is 0. And now we're going to forget the rest of the world and we're just going to live in this tiny little thing that we call the universe of discourse, things I've assumed are true. And yet now this is the hardest part. You have to remember the whole time I'm arguing in this, A is the 0 and B is not 0. I don't know what B is either, but we now know that A is the number 0 and B is some non-zero number. Then if we look at this equation, this is what we would have. I just put them in there. A is 0 and then B is some non-zero number. And also we have to stick that in there. Fact, you can prove this deductively. 0 times x is 0 for any real number. Therefore, I get this string. 0 is equal to b is equal to not 0. So that says 0 is not equal to itself. That seems bad, and this is clearly a contradiction. Hence, we have no solutions in this scenario. So this is the one case where this linear system can have no solution. Long story short, remember, we're going to use this scenario for all larger systems using Gaussian elimination, and then we're going to phrase things with one equation and one unknown as many times as we can and solve bigger systems. So this is important. If you get 0x equals b, that's bad, and there's no solutions. If we reverse it, it'll be all right. Let's do the next case. In case 2, we're now going to let a equal 0 still, and then now we're going to switch for b also being equal to 0. In this case, we're going to get 0x equals 0, but 0 times x is always 0, and this is going to be true, therefore, regardless of what x is. Well, I can pick any real number I want, and it turns out there's infinitely many real numbers, uncountably infinitely many, in fact, which is larger than the number of integers. That's a different video. So this statement is what we call a tautology, or universally true. 0x always equals 0. So regardless of what kind of x I put in there, if I pick 2, well, 0 times 2 is 0. If I pick pi, 0 times pi is 0. If I pick e, the number e, not the letter e, then 0. It doesn't matter what real number I picked, I'm going to get 0. And in fact, I can put the letter in there if you want. We phrase it as 0 times a is 0 for every real number a. My point being is, whatever real number I put in there, I still have that it's a true statement. And so when we start using this scenario for solving huge linear systems of equations, this will tell you the case where I keep saying it, when we have infinitely many solutions, you'll get a row where you have 0x equals 0 or 0 equals 0, which is a universal tautology, which means whichever variable it was free to be anything in the real numbers, and therefore that's what we call infinitely many solutions. The whole moral of that scene was, if you get 0 equals 0, there's infinitely many solutions, and at least one of your parameters or unknowns is a free variable. Let's do the last two cases. All right, case 3, we're still looking at a one equation and one unknown. Yeah, how did you know there was 4 cases and I spent 20 minutes doing a video on one equation and one unknown? Haha, I can talk a lot about math. Now in this case, we're going to assume a is not 0, but b is 0. In that scenario, we're going to get this, ax equals 0, because I know b is 0. And because a is not 0, again, I'm relying on the fact that you know something about real numbers. Every non-zero real number has a multiplicative inverse, and therefore R is a ring, which is called a field because of this property. So it has some nice structure. I'm going to start using this symbol, a minus 1, for the inverse of a. You probably know it as 1 over a, called the reciprocal of a. 2 times 1/2 gives me 1. That's going to be extremely useful, and I'm going to try and mimic it with this horrible thing called a matrix, a rectangular array of a bunch of numbers, and we want to find an analog to this a minus 1 guy. For now, the inverse of a exists, so I can multiply both sides of the equation. Technically what I'm doing is this: I have ax equals 0. We're taking that whole equation, depending on how you've seen this before, but I'm either multiplying the whole equation by the inverse, or it says what you do to one side, you do the other side. And better be on the left again this time when we multiply with matrices to the left. Always. Don't try and do this because they're not commutative. What? You'll see in a few videos. Therefore, what does that do? That now says that I can solve, and these will cancel each other. 2 times 1/2 will cancel. That's the whole point. I want x by itself. We're solving for x. And that's the actual algebra I just did in my head. So if you want, I'll do it again in a second when we do case 4. But I solve for x, get x on one side by itself. In this case, 0 times anything is 0, including the inverse of a also. So we get a unique solution, which is called 0. The moral of the story is, if a is not 0 and b is 0, this is okay. That means you get a unique solution, which we call the trivial solution in mathematics. So trivial means 0. You can sort of just delete it from your memory, the 0 solution. So when you see trivial, we mean the 0 solution. When he says find not, who's he? I'm going to guess in my mind Mark Solomonovich. Whenever he asks me find a non-trivial solution, you can replace that with find all the non-zero solutions. The 0 solution isn't very useful to us, so we want the non-trivial ones. And they should have just stuck to the word 0. But let's do case 4. Okay, the home stretch, we're almost done talking about one equation and one unknown. Then we'll do one equation and 2 unknowns. You think it's going to get better? We'll see. In the last case, if they're both not 0, that's probably where you thought I was going to start off with, and why did I do the first 3 cases? Because those are the important ones. That now tells us in all scenarios, when you get 0 equals 0, that's a tautology, infinitely many solutions. When you get 0 equals non-zero, something went wrong and there's no solution to that system. And then when you have A is not 0, but the B is 0, you're always going to get the trivial solution. And that's not very interesting either. You don't want it to say, I wanted the population to be this and we found out it was 0. It's like something, that seems bad also in most cases for the real world. So we don't want trivial solutions either. What we want is unique non-zero solutions or non-trivial solutions. And then now finally, this is where we're starting. If they're both not 0, there's the equation. Solve for x, or where is x? There it is. That's not what we mean. Isolate x in any scenario. X stays on one side by itself. Everything else comes to the other side. I'm going to do this in overkill and then tell you why I did it in overkill. So first, let me do it in overkill. A is not 0 because I've assumed this. In my universe of discourse now, they're both not 0. This means that because I know something about real numbers, A minus 1, which is 1 over A, exists. And now I'm going to use this avatar, this algebraic avatar instead of this one. You like that one more maybe, but I'm going to mimic when we need the avatar for the inverse of an n by n matrix. A is not 0, his inverse exists. That means I can solve for x. I start off with ax equals b. I've left the space specifically because now I know I'm going to, what you do to one side, you do the other side. So I'm picking a minus 1 who's not 0, and I multiply both sides by a minus 1. Now technically speaking, everyone nods their head, and this is an axiom for the real numbers. If I have 3 real numbers, x, y, z, unknowns, then x times y times z is equal to x times y times z. This is called the associative property of multiplication. What? Yeah, everyone nods their head, but here's where I have to use it. I can associate the brackets and move it to here. So I'm going to do that. It's the only move I did, one at a time. And then we have another axiom in which we're definitely going to want to mimic. 1 times somebody is somebody, and if A is not 0, the inverse of somebody times A is equal to 1. And that's what I'm about to use right now. This guy, this is 1. And then what happens to when I multiply something by 1? Nothing. So this is if and only if 1 times x equals A inverse B. And what does 1 do to it? Nothing. So I can technically write x equals A inverse B. Or you were going to be like, yes, you were probably going to say this. X is B over A. Why did it take me so many steps to get the same thing that you concluded? First of all, I know that math is a house of cards. Once I have the axioms of the real numbers, those never change. Whatever else I have in any move I'm ever going to make are going to be using these axioms from the real numbers. So first move is multiply both sides by this guy, which doesn't change anything. Then I associate, which doesn't change anything. Then I see that A inverse A is 1. And then 1 times x doesn't change it. And then now I have my unique solution, which you're going to call B over A. Why am I doing all these steps now? If I mimic this for the idea of the construct you've never seen, I'll just sneak it in for you, but there's going to be some horrible guy called this, an n by n matrix. And then we're going to get this weird equation that's going to look like this. Don't worry about the details. But then we're going to have to get some horrible conditions and ask, does he exist? And if he does, then we're going to do this. We're going to multiply both sides by the inverse on the left now, on the left. And then we're going to associate. Can I associate matrices? Yeah, you can. So we'll go through that and everyone will nod their head. And I have A inverse B. And then who's he? Oh, we have this thing that A times A inverse is the identity matrix, whoever that beast is. And then we have to discuss who that is. And you get so lost for the forest of the trees, you can't remember why we were doing this. So I could do this game eventually, but we have to define all these things first. Then what happens? Well, that the identity times X, which is A inverse B. And what did identity do? Absolutely nothing. And then now I have all n unknowns in a huge system, and I'm using the exact same strategy for the 1-by-1 system. Don't reinvent the wheel. Just use the same wheel to do other tasks. Please subscribe right here. Hit the notification bell. I'll see you next time.